Hello community! Today we talk about some development in artificial intelligence. So we start with what's on today and what could be tomorrow. Let's start with the most simple example, image classification. We have two functions. Remember, we have a score function that maps the raw data to a class score, and we have a loss function that quantifies the agreement between the predicted scores and the ground truth labels. It is an optimization problem in which we minimize the loss function with respect to the parameters of the score function. And if you read a sentence like the blue sentence on the top left corner, we define a function from the pixel values to class scores, which was parameterized by a set of weights. Well, what does it actually mean? On the right side, I'll show you an example. We have a training set of 50,000 images, 32 pixel times 32 pixel RGB. And we have 10 distinct classes. I want to know, is this object in the picture a cat, a car, a house? 10 classes. So we define now a score function f from r times d to r dimension c that maps the raw image pixels to class scores. This is the most famous equation you know in artificial intelligence. For an image xi, has all of its pixels flattened out to a single column vector of shape d times 1. We have then the matrix of the set of weights of the size c times d, and the vector or bias of the size c times 1, and those two are the parameters of the function. So xi contains all the pixels flattened into a single 3072 times 1 column. The weight matrix is 10 times 3072, and the result is we put in 3072 inputs and we get 10 output classes. So this is here a visualization from Stanford Spring 2022, a beautiful course. This is the URL. Go there, have a look at it, and you see how easy this formula can be interpreted if you look at it from this perspective, that you have two functions, a score function and a loss function. And I think what we're going to do next is we're going to talk about the loss function in a little bit more detail. Again, remember, the images, the pixel of the images are stretched into a high-dimensional column vector, and we can interpret each image as a single point in this high-dimensional space. We have a 3072 dimensional space of our 32 times 32 times 3 RGB pixels. Also, the entire data set is a set of points. And since we defined the score of each class as a weighted sum of all image pixels, each class score is a linear equation. Let's have a look at it in detail. The goal of all this optimization of our AI system is to find a set of weights W that minimizes the loss function. How we do this? We want to find a direction in the weight space. And please remember, it's the weight space that would improve our weight vector and give us a lower loss. The loss function is called as a cost function or the objective, but we are here in the gradient of the loss function. There's a beautiful description here. You can read it. Have a look at the homepage of CS231N. They explain it again in detail, but if you really want to have a beautiful YouTube video, have a look at 3 Blue, 1 Brown. The title is Gradient Descent, How Neural Networks Learn, Chapter 2, Deep Learning. It is amazing if you watch this movie, if you see how all the different weights and the different hidden layers adapt if you do gradient descent for image classification. And it is a beautiful, beautiful visualization. You should have a look to really understand what's going on. Now, another today is that you think that we need just something about probability and statistics, but no. The way forward is, I think, coming from physics, theoretical physics. And a beautiful example is here the principle of least action. And it is the classical notion of a single classical trajectory of a system that makes the jump to a probability amplitude. So the probability of an event is given by the squared modulus of a complex number called the probability amplitude. And if you add together the contribution of all paths in configuration space, you get the probability amplitude for a certain event. And the contribution of each path is proportional to E times IS, where S is the action given by the time integral. So this beautiful idea of a probability amplitude by Richard Feynman was introduced, I think, in the 1950s in theoretical physics, but I think it will have a second life here now when we try to calculate multi-class artificial intelligence systems that are dynamically coupled and have some highly interdependencies. Now, the path integral assigns to all the amplitudes equal weights with a varying phase, or the argument of a complex numbers, and a contribution from paths widely different from the classical trajectory might be suppressed by inference, but the path integral formulation of the quantum field theory represents a transition amplitude as a weighted sum of all possible histories of the system from the initial state to the final state. And if you know a Feynman diagram, this is a perturbative contribution to the transition amplitude. And if we take this idea that comes from theoretical physics from the 1950s, you can see that even today, and this is from Archive, this is July 26, 2022, the existence of real-time quantum path integrals. And now they look, there's a Wick rotation and something on, to the new developing field of quantum paths in artificial intelligence. So this is a hot topic. You see the flames, beautiful. But I want to show you, normally we have a dynamic system. We have boundary conditions. We have analytical solution to the system. We have clearly defined inputs, outputs. We have no chaotic correlation. And we have no intertwined dependencies within the system. This is a classical system approach that we have today. But if we go forward and we want to predict complex interactive systems, have a look here. We have 4 dynamical systems that are highly interactive, that have time thresholds, that have interdependencies, that have hidden parameters, threshold manifolds. So you have to look at all the different paths possible. And this is where this beautiful Feynman path approach comes in, I think, to artificial intelligence to enable us to do something like a gradient descent on a much, much more complex level. But I'm not sure that the mathematics or the code for this system has been developed yet. But what we have, in green you see what we have, in red are the problems. In green, we know about gradient descent. We have the physics of quantum field theory. We have system-specific ground truths, but just for single systems. And we know something about the eigenflow. But we do not know about multiple dynamical systems, how we map them to AI prediction. We have interdependencies we don't know. We have no ground truth, and we have hidden parameters we don't even know yet. But we have with AI a system that is possible to have millions of degrees of freedom and millions of interdependencies that the system should map. Feynman paths will change dynamically multi-system AI.